How's it going, everybody? The full title of this talk, which doesn't fit on the slide, is I've got the non-photo blues, or how this moment may be the nadir of color reproduction accuracy in digital video, but this is better, and it has a U, and it has a U for a significant reason. Let's talk about non-photo blue, which was in the title. Non-photo blue is a shade of blue that's used by illustrators because it's invisible to photocopiers, mostly invisible to photocopiers. The old like drum style where you have a backlight that energizes toner. Here's an image. It's invisible. You've seen like drawings like this, where they've got the blue sketch in the background, and this is with a normal scanner. But for some like miracle of physics, like I tried to find the answer to this question, and they're like, nobody knows. People do know. Like it's something complicated with electromagnetic spectra, but nobody's like writing it down. So this is, the point of this is like color is hard. A lot of this shit is magic. You just don't understand why something happens. You'll try it and then it won't work. That in mind, I'm also like not a world, yes.
Why did the last slide not have a U?
What I'm trying to set up throughout the talk is a larger theme on the inconsistency of color reproduction throughout various media. And therefore, somewhat intentionally, decided to write color sometimes with a U and sometimes without. That was total bullshit. You can't tell. Yeah, okay. So there are actually books on this. I'm going to go buy them. I just found them recently. A lot of this came out of, so YouTube's doing HDR. And HDR has a new Colorspace and everything's we realized how badly we're doing it. We're not the only ones that are doing it badly. When you looked at FFmpeg, when you looked at anybody who grew up in the open source community for video, and that's a lot of us here, color really like doesn't work. Part of that's just because accurate color equipment is expensive. It's unnecessary when you're working on a $500 shoot. A lot of the things that open source shoots for, in its mentality of let's get this done inexpensively, let's make it democratic. Fine color calibration requires expensive gear. And so a lot of people in the open source community just haven't had access to it. And I found that in talking with a lot of people, it's a common thing to get wrong. Now, that said, they're in good company because pretty much everything has something wrong with color. Even if you look at professional color grading software like DaVinci Resolve, it doesn't set the flags properly on export. We're entering into conversations with them, but like, there's something wrong with everything. You just have to get it right. In professional cinema chains, the way they've made this work is not by standardizing everything and then getting everything to work correctly with each other by signaling. It's by having really talented people who can spot what's wrong, come and fix everything. And that isn't really scalable. I reordered the slides. The reason we became interested in this is because we announced HDR. And as part of HDR, HDR has a wide color gamut expansion to the profile. It's more than just dynamic range, it's actually color as well. And when color was pretty wrong on YouTube sometimes in certain circumstances because we weren't really paying attention to this. But with HDR, it's like way wrong. It's inescapably wrong. And so we actually started to pay attention to this and have to realize that we need to fix it because there's a new normal. Let's talk about the old normal. Old normal is BT709. This is fully spelled out, ITUR BT709-6 or Rec 709. The -6 is the most recent standard, but if you just Google BT709, you can find a link to it pretty quickly. It's like 5 or 6 page standard. It's worth a read just to find out all of these new words that you don't know. The important parts of Rec 709 for color are the OETF, the primaries, and the YUV. One of the -6, which was released like a couple months ago, is because they used to call OETF like transfer function or like transfer characteristics. There are a bunch of names for it, but the modern name, now that HDR has come out, is OETF. Let's talk about this from the camera perspective because it's illustrating to know how irrelevant the camera is to this. The first thing that matters to color when you're going to shoot a video with a camera are the color filters on the camera that sit in front of the sensor, and then the sensor itself, which will have different response characteristics. And those are really complicated interactions with color. They're usually not precisely aligned to any standard. And then further complicated, most cameras use a Bayer pattern. So in order to they have so many pixels in their rated sensor output, but they're not 3 subpixels per pixel. Usually they have more green primaries than blue or red, and they use that because human eye is more sensitive to green, and we'll come back to that later. And then that needs to be reverse processed into pixels that end up, conceptual tristimulus pixels that end up in a grid that go onto a display or go into a JPEG, because that's normally how we think of color, not in a Bayer pattern. So all of these things, the color filters, the camera sensor arrays, the debayering process, it ends up being called a term color science in general. So like if you get red, you can say, I'm using Dragon Color Science V2. It's just not, this is not science, but it is a package of things that people who are familiar with science have made, but it has a lot of artistic intent as well. It also tends to have a lot of bugs, which you just have to deal with. It's like you'll find, I know one colorist I was working with recently was like raving about how easy Ari was to work with, and it's like Dragon's color science is all this. So people have opinions. It's not a science. The last piece of this is the OETF, optoelectrical transfer function. Now, in theory, what this means is it's the rate of photons coming into the sensor. We say rate rather than just number because it should be relatively constant despite frame per second changes. But then it tells you how to map that rate into numbers. And so you can say like a certain luminous intensity from the sensor becomes a certain value. That value is gamma encoded. I'm not going to go into this there. There are a ton of great articles that compare like SRGB and gamma. HDR is going to have to rewrite a lot of this as well. Maybe this might become a separate talk. For me, you can definitely find a lot of articles on the internet. We're not going to go over that there. It's a great idea. We should do it. We do it. It causes problems when we do it. And the result of all this is that you don't get anywhere close to accurate. So when you actually take a camera and capture a scene, it tries to do a bunch of adaptive things to make up for its limitations, and then put all of that into a standard representation which is dramatically different from the underlying properties of the sensor. It's applying a bunch of compensation functions to give you a relatively consistent and easy to work with image, but this is not like a scientific process. You're not taking a reading, putting it on a scale with absolute numbers. Basically everything with a modern camera is relative somehow to some color space setting, to a white balance. So this isn't about finding a true match to color, which makes it hard to produce accurate results. Now, one way around this, sort of, is to use a color checker, commonly called a Macbeth chart. It's some of these, it's brightly colored squares. The problems with this are twofold. One is it looks completely different here than it does here. And two is that even when what it looks like on here looks nothing like it does in real life, because of all of the problems all the way from the display chain to the capture chain, the colors just aren't right. And that problem is complicated by the fact that even if you can calibrate it, even if you load it up into your color grading software and get everything perfectly right, this is only true from the light that's shining on it. And in the scene, you can see like this particular scene, there's a tree over his shoulder. We don't know what that tree is because there's not a color chart in front of it before they do. You'd have to calibrate each part of the scene differently in order to get the true color of an object. Because the true color actually is a function of the light hitting it. Or I mean, not the true color, but like the spectral response of an object and the spectral response of the light hitting it. All of these things are complicated by the fact that pretty much as soon as you get this into the color grading suite, people are going to mess with it because they want a certain look. If you look at the best looking content that we have, almost all of it doesn't look anything like what is shot on camera. If you're watching Game of Thrones, like, they're not traveling worldwide. They're not using different stars to illuminate their sets. They're going to their color grading process and deciding that they want a certain look for, okay, we're on the wall, so it's gonna look really cold. It's not that cold. It might be a little cold, it's not that cold. So the idea of color accuracy from camera to monitor is pretty much bunk. It starts in the color grading process is where we really have to preserve artistic intent, where we have to trust the colorist. And that's interesting because a lot of times on YouTube at least, like, we didn't have a colorist as part of our process. So we were just assuming that our goal was to preserve everything, and it's really not. It's to make everything look good. which that's a challenging argument for YouTube where we just have an upload button. It's a really complicated conversation. It's not like, I'm not announcing a big change in policy or anything. We're gonna, for the time being, we're gonna continue to just pass files through. But there's a lot of room to consider options there. Okay, so let's take that process in reverse and consider it from the perspective of the actual display chain. The OETF is intended to be the inverse of the EOTF. They're both symmetrical pairs. So when you're talking about you have an input amount of pixels hitting the sensor, converted to a number. This one's from what number do we have a certain number of photons leaving the screen. And as we've established, this is totally not realistic in any meaningful way, but it does matter to get this right because, especially with HDR, but even with gamma curves and stuff like that, it will affect the color reproduction, it affects the overall feel of things. There are a lot of ambient characteristics that matter for this to get the right feel. But again, that's like a whole second talk, so we're just focusing on color. In the color thing, only apply this to RGB. This is not, like, do not run your transfer function on YUV. I know there's been a lot of confusion on this. So the pipeline is you have an input sensor that converts things into color values. Typically those color values have been converted into an RGB color space. Those are linear values typically. And then you like apply a transfer function, like the gamma. And then you do a YUV transform. And then you reverse that. You YUV to RGB, RGB to linear light RGB. So typically we write like R prime, G prime, B prime when it's not linear light, if you have to distinguish the two, but we usually forget. Sometimes RGB means XYZ, TCP sucks. The HDR transfer functions are highly nonlinear, so this matters a lot more to get the transfer function correct. It matters more for things like scaling. Like you might find in some of the talks about gamma and transfer functions that they'll talk about the distinction between scaling and linear light versus scaling and gamma. Scaling and gamma is the wrong thing to do. It's worse in HDR color spaces. Just don't do that. So now that we're talking about that, we have in Rec 79 another component of the notion of color are the primary chromaticity coordinates, or we just call them primaries. And these are the 3 points on this triangle inside a color space. So let's talk about what's going on here. This is a representation of the XYZ color space, or CIE 1931. CIE is some French standards body that has a bunch of color measurements. You'll see some interesting features here. One is the spectral locus. So each of these numbers, those are wavelengths of incoming light. So we perceive light at 380 nanometers to be that color, the one down on this one. The color's not accurate because, of course, screens, modern technology, nothing works. But it goes all the way up through the greens and then out to the reds. Anything in the middle, that's not one frequency. So a very limited, very super saturated set of colors are all the way around the edges. But if you're talking about like pastels, if you're talking about anything that's not mega saturated, including like a lot of greens, yellows that are inaccessible via primaries, those are all blends of colors. And the interesting thing is, there are multiple ways to get there. So this space is sort of additive. It's not really Cartesian in any meaningful way, we'll get to that. But you can get to a point here by adding some of this light and some of this light and some of this light. And normally what happens is you'll have a complicated spectrum of colors. And the complicated spectrum of colors will evaluate in the human eye to a single value somewhere in the scale. And the process of converting a spectrum to an XYZ color is really complicated. Basically it involves getting a human to measure it and to compare it to something else, which is an interesting property of all of this. One catch is, I've been talking about XYZ, and typically we use XYZ literally to refer to this chart and stuff like that. This is a transformation of the XYZ space into something that's more easily chartable. It's called YXY. So you've got the lowercase x and the lowercase y on these axes. And then the capital Y is brightness, and that extends into the vertical dimension. So normally we talk about things as having consistent brightness. But when we're talking about like color primaries, we're thinking of the big Y, the brightness value at a certain position. I mentioned spectral locus while the thing was on the screen. That's the outside line. It's the spectral locus where it's a monochromatic frequency. And everything is a spectrum. The term for any color in the middle, so the equivalence of any two colors that have different ways of composition. So like you could have, green is, yellow is like a green and a blue. But it could be a slightly different green and a slightly different blue and work out to be the same yellow. So there are a lot of different ways to get to each color because spectra are really complicated and colors really aren't. And that term for the equivalence of all of those different colors under different frequency spectra is metamerism or metamerism. I've also heard it called. I don't know which one it is. But I'll go with metamerism. So when you have a metameric match, it means that you have two different spectra, but they're perceived by the same, as being the same color. Now, when I say perceived, I mean perceived in the CIE 1931 color space, which, interestingly, how it's derived by getting a bunch of colors that are different with different spectra and having people twiddle a knob on a reference color made up of different colors to try and match the one color to the next color. And they did that with just piles and piles of colors and made a big table cross-linking everything so you could find how to match colors between different frequency spectra. Yeah?
So you say there are two things. One is you say RGB is not a Cartesian space, which means we would, as computer science, to decompose any color into the RGB like components, that's artificial.
Yes, so to be clear, not only RGB, but XYZ, CIE 1931, what we're talking about here, which is like you typically think of RGB is either, even linear light RGB when we do merges like that. If we're talking about color equivalencies, RGB, like if you have red 50 and green 50, it's not the same as, how to express that? Well, so every color in RGB is distinct, but the differences between the colors, if you're performing a scaling operation, where you take two adjacent colors, we'll actually get to this in a second, take two adjacent colors and average them. It's not the same perceptually as if you would have the two colors presented and just be so small that the eye merges them because of the focal length. So the two different spectra end up evaluating differently than the average in RGB space.
So what you're saying, there's no linear operator that can work in this space, but there can be some nonlinear operator still connect because each element is still uniquely representable. It's just the relationship between two arbitrary colors are strange.
Right, yeah, that's exactly right. So actually, I'll skip ahead and then skip back. What you're talking about is so this phenomenon of you can't average two colors because the averaging in the eye is different. There is a space with a highly nonlinear operator. CIE 1976 L star, A star, B star, or more succinctly just CLAB, which I should have put the cartoon in there, but I'm sorry I didn't. That is perceptually uniform. So in this space, which I've got a picture of here, it's the same kind of spectral locus mapping as before, but the insides are all distorted. The colors are approximately right here, but there's a lot of nonlinearity that you can't see when coming from just straight up combinations of colors. But you can perform Cartesian math in CLAB. There's a simpler version called CIE LUV, which is it's still nonlinear, but it's less complicated to transform. It loses some accuracy, but it's much simpler to compute. And the other component that was interesting was there's the twiddling knobs thing about how CIE 1931 is derived. Just to give you an idea of just how whiffy all of this is, that as soon as the color sets that were established, like the equivalences, when they did the CIE 1931 derivations, were on tiny patches in the center of people's field of view. and they realized that people's color perception changes from here to here. And so they ran another set of experiments where they blocked off the middles and had everybody compare the outliers, had a completely different color space. Like, all of this is crap. It's so complicated.
So should I sit in the center of the movie theater or on the side?
It depends. Do you like your colors to be green shifted? Yeah, it depends on where you're looking. Like, it's so complicated. Anyway, back to Rec 709. These are the actual colors, the primaries and white point of Rec 709, which gives us this picture again, just to bring us back to the sanity of an XYY or YXY. Now, when we're actually going to produce one of these primaries on a display, in theory, what we should do is we should make the display with some display characteristics, figure out that the primaries have some spectra. Hopefully the primaries are more extreme than this. And then we sit down and do observer matching. Somebody sits there and says, this green should look like this green, this blue should look like this blue. You build up a whole matrix which kind of helps us understand the capabilities of the display with particular primaries. We can get by that by tossing a bunch of, usually actually we'll convert the display's measured spectral characteristics into L star, A star, B star space, and then make a matrix from there. Yeah.
I hung up on something you just said. If I have, I'm just a poor engineer who won my way through most of this.
Yes.
So I've got my H.264 stream. It's 1080p. I decode it. I've got some YUV. I don't put it into RGB because I'm lazy. And I scale down my YUVs to 720p. I just feed them into X264 again to send it on its way.
Yes.
So I just messed up my colors.
Yes.
Oh dear.
You messed up your colors, but the good news is even if you had converted it to RGB, you would still mess up your colors.
Okay. Great. So what I need to know is there's no easy scale that just kind of says, okay, well these 4 are turning into 1 or maybe 1.5 pixels over here. That's just going to be wrong.
Yeah.
If my function is linear and I'm a plus b divided by 2, I'm messing up my colors.
Yes.
Does FFmpeg have a nice easy way to do this for me?
We're going to write one.
Okay.
It's going to be slow.
So right now, if I wanted to do this right, I'd have to do it myself.
Yeah, I don't think there's anything out there that does it right.
Perfect. No one else is doing this. Great.
Competitive advantage.
That's coming. I think it is wrong. Is it because color is wrong or it's other distortion? So I don't know. It's maybe mathematically it's not 100% correct, but as we eyeball it, is the error more coming from the error curve, error distortion, or it's
If I was a good presenter, I would have prepared examples for you of just how wrong it can get. Sometimes you get lucky and scaling doesn't really matter. Most of the time, people are watching on devices that are worse for reasons that we'll get to than the process of scaling does. There are some times when scaling will completely trash your color. It's worse in HDR where you have larger dynamic ranges and you tend to have a lot of contrast in the shots. But even for normal gamma encoded standard dynamic range stuff in Rec 7 and 9, YUV scaling messes up your colors. It really does. Fortunately, when we're talking about color, most of the time we've got color patches that are largely the same. And so the only points where scaling matters is where you've got adjacent patches of different colors. It's the same reason why chroma subsampling works in the first place. Chroma subsampling is a stupid idea, and we'll get to that. I don't know if I have that. It doesn't mess it up so much that you want to cry, and that's been the crux of this all along. Is that it doesn't completely suck. So people in the open source community, and just generally, have put up with it. But it's getting to the point where it's going to suck more because we are more expressive, because display devices are going to be more capable, and because we've had generation after generation of smartphone that have gotten closer and closer to being able to pull this up and reproduce the real world. And now we're getting to the point where it's not glaringly obvious how bad it is, and so when it goes wrong, we'll ask why for the first time, because we've always had low expectations. So, yeah.
Sorry, back to that topic. I'm thinking when you do the scaling, depending on what filter you use, because there is really no absolute correct answer when you do the scaling.
Yeah.
Is it
Well,
so-
I mean, no, there is. So you convert into linear light, and then you convert into L star, A star, B star, and scale in that space for your chroma components, and then scale back. That would.
Even in LAB though, if you're like Pastor Knife was great for your lower resolution, you have to make something up. Like it's unrepresentable.
Right, and the other great challenge of C-Lab is that sometimes what you make up ends up being an imaginary color on the way back, which is just delightful. So yeah, no, none of this is easy. None of this makes sense. It all sucks, which is why we're getting it wrong. But there are easier initials. Yes,
YouTube's getting this wrong.
YouTube's absolutely getting this wrong. YouTube got this way worse before though.
Everyone is getting this wrong. $300 million feature films are getting this wrong.
Yes.
Very wrong.
Well,
Yes.
I mean, this has been a problem since like the Impressionists. Don't lose sleep over it, right?
Damn it, if only we could standardize indigo blue.
What about macaroni though?
Macaroni's white point is pure. It's not macaroni and cheese. So this white point thing, I've got white point listed here. The white point here in this image is D65. The white point is the point if we set all of the colors, like 50% blue, 50% green, 50% yellow, not yellow, what am I doing? Red, to have those equal values. The white point is where it should end up. We can't match any of the colors in here without knowing the white point. Because you wouldn't know how far, you say like 20% blue and 30% green. That should push it somewhere, but that somewhere isn't constrained by the primary coordinates alone. You also need the white point to figure out how to do that. And that becomes really important for us as video engineers because it defines the characteristics of the YUV transform. So this is all like, now it gets practical. Now we're not talking about random bullshit, now we're talking about how to actually make a scalar that screws up the minimum amount while still staying in the linear space. When we say YUV, we usually mean Y prime CB CR. This means that it comes from, it's digital, which is the CB CR part, rather than like YPB PR, I don't know what the P stands for, or the C for that matter. But the Y prime means that it's coming from gamma encoded, or otherwise transfer function encoded, rather than linear light RGB, which is basically everything that you would want to do. Now, back in the analog days, as we were mentioning, this was really useful for video because it would allow us to use smaller megahertz sidebands. So the FCC had already allocated spectra for different television channels, and they wanted to add color to that spectra. And they put that color information in side lobes, cutting off some of the padding that FCC had allocated so things would hit. There wasn't enough padding in the side lobes to accommodate a full frequency channel. So what they did was split it into YUV. Actually, it was YIQ, which is really similar but has slightly different properties. But YUV, and downsampled the color information. That's because the eyes are much less sensitive to color information. Today, it's dumb to do this because we can still separate things into color and luminous intensity, and that makes sense because the eyes are still, we haven't evolved past our color limitations. But instead of downsampling everything, we should just tell our codecs to compress the other two channels more, and they'll do it much more intelligently than slamming everything with a downsampling filter.
And they're inherently more compressible.
Yeah, that's true. There's less entropy in those channels anyway. So you just use the large transforms in modern codecs. It'll just smash that stuff down. We should be doing this. We should never allow YUV444 or anything other than YUV444 or RGB. Yeah, what's up?
So is there any, from my understanding of codec, it's usually focusing on the Y, so whatever motion decision that made on Y sort of implicitly or explicitly applied on the U and V.
Mm-hmm.
So is there any theoretical study that if we do these compression in separate channel, as you suggested, that it will give us better compression or worse compression?
I don't know, Alex.
I was going to ask a different question.
Do you have the answer now, or?
No.
No, okay, then I don't know.
My answer was about YUV 420 versus 444.
Yeah.
My users complain that the 444 version of our codec is twice as slow because it's handling twice as much data. What should I tell them?
Make it faster.
I feel like that's what you're telling me. And I want excuses.
It's worth it? How about it's worth it? The color artifacts, especially HDR screws this up. So chroma downsampling, flat out downsampling in the chroma space is much worse in HDR spaces because adjacent colors are encoded non-linearly, and that it's going to be worth it in the end. But you know that's that's VP10 timeframe when we're going to fix that. This is not a VP9 thing. So I will bring you some test samples and we will have this conversation soon. As an aside, in case you were wondering if this magic transform is actually destroying everything, it is. The RGB cube fits inside the YUV cube, which means necessarily, if you're still using 8 bits for this, it's aliasing colors inside of the space. So even just converting to YUV and back, the transform is lossless in floating point. It kills colors in whatever. So if you actually pop open a histogram filter on an encoded video, you'll see a bunch of notches in that filter, and it's coming from YUV because it's aliasing colors. Now, the derivation of white point and why, this is all in the spec. I've got some examples which I'll toss up in a repo that I guess we'll mail out or I'll post a comment or something like that. There's this amazing library called Color with a U for Python. I totally recommend checking it out. It does almost everything. The only thing it doesn't do is YUV conversion, and this is basically all that you need for this. So this is the white point locks down some coefficients in this matrix, and you can derive one from the other, and then this code does it for you. So primaries, white point, EOTF, and YUV matrix. This is a modern color space, and our job now as video engineers is to get this from one side of the display chain to the other unharmed, except white point is usually implicit, so everything's ruined. Fortunately for the 3 standards that matter most to us as internet video engineers, which are Rec 601, which we'll get to, Rec 709, and the future Rec 2020, they're all mercifully use the same white point, so we don't have to worry about complicated things like a chromatic adaptation matrix. The white point is D65, which is derived from sunlight. It's cool to go read the Wikipedia article on this. We don't have time. There's more to cover. So D65 is the white point. It's really close to 6500K, which is why the name is, but it's not quite the same. How is this conveyed in our video files? So when we say Rec 709, well, we actually split it out explicitly into color primaries, transfer characteristics, and matrix coefficients. Color primaries, these are the official names for these things in all of the specs. So color primaries are the primaries, transfer characteristics is the EOTF to use when you're decoding things, matrix coefficients is the YUV parameters that you use. In H.264, H.265, this is contained in the VUI, Video Usability Information. This is a supplementary message, an SEI message, that gets tossed into the stream. You should do your best to preserve it. There's the NCLX atom in the container of BMFF or MP4. Now, technically, that only references a few values in JPEG XR or something like that. WebM will, usually next week, I promise next week we will have published the updates to the spec to have all of this in WebM as well. Right now, you kind of have to rely on a single value which represents all of these things, which doesn't, there are sometimes you get a file with 709 transfer characteristics, or 709, transfer characteristics in primaries, but like a 601 matrix or whatnot. There's a new spec, it's called Coding Independent Media Description Code Points, ISO 23001-8, which lays all of these out, all of the new ones, in a way that everybody can reference. It's a really simple spec. All it does is map enum values. So you say 17 is Rec 2020. I don't know if that's right, but you can find out pretty easily. I don't know if you know this trick, but search for free ISO specs. When you search for the spec name itself, ISO has, for some reason, anti-SEO optimized this page. I don't know what the reason is. But you can go and totally legally download most of the standards that you need right from this page. You just have to search for free ISO specs, go to the page and then search for the spec. Now, why is everybody screwing up Colorspace in particularly open source video, which is mostly where I work? The problem is YUV matrix. So what happened is we got a different spec long ago for SD content, Rec 601. So as things started coming in, they started being Rec 601. The spec is really old. It's different in the EU versus the US and Japan, like NTSC PAL differences. It's limited, it's smaller than anything that we have in modern days. It's based on old CRT technology, so just don't use the spec. The only thing that you should ever use the spec for is reading 601 values out and converting them to 709 to send on to a modern display chain, because basically nothing is native 601 anymore. The problem with this is the 601 and 709 primaries are really close, but they used a different matrix. And that means that the wrong matrix was more common to find in different YUV encoding parameters. Because literally, if you Google YUV matrix or YUV conversion, most of the results on the internet are for 601. Just by quirk of fate, most people use 601 rather than 709. And this has persisted all the way to today, so by default, a lot of software uses a 601 matrix. It's a really interesting quirk, but it has completely screwed us over, because the color shift is actually pretty noticeable just from the matrix differences. It will make, some scenes, if you go one direction, it gets really green, the other direction, it gets really magenta. And so between that obvious fix and the fact that it's numerically really easy to verify if you got this right, because you end up in the right averages of color spaces and whatnot, then that meant that most 601 files could be fixed by converting the color matrix back to 709 before decode, because the primaries were really similar, the matrix was more different. Unfortunately, this means that in people's minds, the YUV matrix alone became the thing that you convert when you converted color space. You didn't actually have to do the primary conversion, and you don't really. You can get by without doing the primary conversions for 601 and 709. But that means even in things like FFmpeg calls the YUV conversion matrix the color space. That's the internal variable name for this. It's not, it's just the YUV matrix. So that's fundamentally wrong, but it's a practice that everybody is messing up. We were doing this at YouTube. We were thinking no, it turns out it doesn't work like that. Color space conversion minimally requires all four to do accurately. Sometimes it even requires, if you're trying to convert a reference color in one environment to be the same in a reference color in another environment, you need to take into account more parameters, including ambient light, the position of the monitor in front of the screen, all the stuff that makes colors such bullshit to work with. Rec 2020 breaks all this down because the primaries in Rec 2020 are vastly different than the primaries in Rec 709. Rec 2020 is big enough to encompass basically all of Pointer's gamut, which is somebody went around and measured every color in the natural world. Pointer was his name. And he drew it out on the grids, and every color that we know falls inside this grid. And Rec 2020 encompasses 99.9% of this. So the primaries are necessarily really wide. I'm really excited about Rec 2020, but it's gonna, it breaks everything because we actually really have to get it right. HDR breaks it worse because now different adjacent colors can be such dramatic different intensities, and often are, to show off HDR as people still get their hands on this thing. So as we get new displays, everything breaks. So just kill it. So we really need to redo this. The other thing that really makes Rec 2020 just incredibly challenging is everything is on the spectral locus. So in theory, in order to produce a perfect Rec 2020 display, your display needs to emit single wavelength primaries. Its green needs to be exactly, I guess it's red, needs to be exactly 630 nanometers. There's no getting around that. You need to build a display one way. And it turns out, you'd think, oh man, finally our problem is solved, we don't have to compensate, we don't have to calibrate. It makes it worse. Because monochromatic primaries have metameric instability. When you show a color with monochromatic primaries that you think should match up, in LAB space or in LUV or in any of the spaces that we know about, if you really use the purest colors and then put them next to a monitor that we know can display the same color with a metameric match to another monitor that can display the same color. So these are all in like the middle of the range. The one that has the pure primaries will be wrong. Well, and we're still working out the details of this. Actually, somebody just sent me an awesome research paper that I haven't finished reading because I was busy making slides for this talk. That went into how like he broke it down and he did a bunch of calibrations and how. So there's a research going on how we can fix this. But that doesn't really solve the problems of metameric instability on the surface. The other problem is even the brightness. Like brightness is something that we pretty much had a lock on for a long time. And with these monochromatic primaries, the brightness can vary a lot. Now that's mostly because they're using freaking lasers to generate the first display, but it has perceived luminance instability. Part of this, the reason why this is a problem and isn't, is because Rec 2020 was originally intended to be a container format. It was supposed to be like you had DCI-P3. It's the primaries for the cinema displays. Which are larger than 709 but smaller than Rec 2020. It fit inside Rec 2020. So a lot of cinema content was made for DCI-P3. And those would all be like multispectral colors. Those aren't on the spectral locus. And the idea was Rec 2020 could accommodate that and maybe a little bit more. But they picked colors on the locus for simplicity, not really thinking that people would ever make displays like that. Being consumer electronics manufacturers, immediately all the device makers went to make that and ignored the advice, and so they started looking into technologies like quantum dots. Yes?
I didn't understand metameric instability. Is there like a simpler version? Like, what I heard was, there's a TV that's showing me a red that is a perfect red that is basically only activating one set of cones in my eyeball, but my brain doesn't understand. Is that, am I wrong? Was my understanding wrong?
I'll just Google this. So one thing to know here is well, hold on. If I can type. Not sure.
What have you been doing lately?
Yeah. Whatever. So if you had a pure red, you actually see it's not just activating one broader color.
Right.
It's activating multiple of them and giving you different colors. The problem is, if it's tiny, then it's going to activate different cells differently because
Oh, so it's like the average of my cells.
Right. So they're actually like it's protein folding that governs the shape of the response function of the cells in your eyes, and protein folding happens in different, even if you have the same gene. So people with color blindness have slight mutations which cause the proteins to fold differently, and those respond differently. But the proteins themselves activate differently depending on pH level in your eyes and whatnot. And so having a spectrum gives things a little bit smoother response. But when you have like a tiny narrow monochromatic frequency, it's like, you know, when you look at a laser and you see all that shimmer. I don't know if that's true at all, but I'm imagining that it's true. That people's eyes are just responding differently. I think there's another reason for that. I need to go look at that. But you get what I'm saying. Like, you can imagine like a laser shimmery thing.
I was told never to do that.
Yeah, okay.
Pilots love it.
Some of us sacrificed our eyes for the cause. So we're almost done, I promise. So the monochromatic primaries,
There's
and
weird.
human biology, like again, like everything is screwed up. 10 degree is different from 2 degree. Monochromatic is different from the equivalent. We don't know yet. We haven't fully modeled the human brain and the eyes that see it. So quantum dots are cool. You can read about them. I'm not going to talk about them here. OLED does it directly. OLED actually will drive to a particular spectral response without any intermediate filters or bypass necessary, which is great because OLED is not just for stupidly expensive TVs. My phone is OLED, and my phone actually has phenomenal display characteristics. Its primaries exceed the DCI P3 gamut. This is better color than you would see in the best of movie theaters. On my phone, for free. Nobody was even really paying attention to this. Samsung just happened to make the OLED primaries, and they happened to be out here. And they were like, oh crap, maybe we should, use them for something. Actually, that was us. We did that. So we're going to ship this on mobile for HDR with white color gamut. And it makes a lot of sense for HDR because you can get really great contrast with OLED. You can drive the display all the way down to 0. You can dither effectively, even though the pipelines are all like 8-bit internally with gamma mapping. With the right dithering, you can do a lot. That for another reason, that's the expanded capabilities are a big reason why we think that there have been rumors about the iPhone and iPad switching to OLED displays, despite generations ago Apple was trash talking OLED, and rightly so, because without color calibration, without a lot of the color science that you put into it, real color science, not like color science, that they weren't capable of doing things accurately. But now they have decent longevity. Nobody keeps their phone longer than 2 years anyway, so so the longevity issues don't really matter, and they have great color response. So they're likely to be in most mobile devices. The problem is the wide primaries mean that everything needs to be carefully calibrated for the display. If you have an image coming in, usually it's going to be in something like SRGB, which is basically Rec 709 with a slightly different transfer function. And Android ignores this. So the color on my phone, I don't know if somebody wants to pull up like a SMPTE color bars, just search on their iPhone versus, I'll do the same on this one. And we can look at it after the show.
How do we spell
I'll wait
SMPTE?
for that. SMPTE. And what you'll almost certainly find, click on the third one, which has the brighter colors, and they'll almost certainly be dramatically different on that phone than this phone. Sorry, I meant to have somebody do this before the show. But you can see just like vastly different colors there. And that's because my phone's ignoring like the fact that its screen has these ultra white primaries. So we're going to need to do, I can skip all this. We're going to need to do like color space correction in firmware, and that needs correct metadata at every level. When we read a picture in,
Sorry, just to understand your point there. You're saying that although the display of your device is fantastic, Android is not taking good enough advantage of its capabilities?
Right. So Android is taking full advantage of its capabilities, despite not realizing that to do so is to shift the colors way out. When really what Android should be doing is, unless it's told otherwise, it should be clamping them back to the same capabilities as the iPhone, which kind of sucks because you get into a place where you built a beautiful display and you're not using it to its full potential. But the alternative, which admittedly doesn't sell phones, is you pack everything in, you have accurate color reproduction, and now you need to convince everybody that because it's the same as an iPhone, it's better. Like, why would you do that? You want one that's more vibrant and saturated and ridiculous and stupid, but that's what people do.
Right, so it's capable of displaying that weird green right out on the edge.
Right.
It shouldn't.
It
But
should,
then when you
unless
just
it's
put
told
like, 02550, rather than like putting it in the right triangle, it just like puts it out there on the edge.
Right. It's not right on the edge, but it's much closer than an iPhone screen. Exactly.
Right.
But sort of what you're also assuming there is that the content production workflow before the media's got to distribution and to your device has actually maintained colors in the right way.
Exactly.
And that almost never happened. Even going from your beta pattern to an RGB color space, who knows what magic is going on there? So how can you ever make sure that your color is right?
Right. So then, so you have to maintain, like when you have your input signal, you have to have flagged it correctly. It has to be the same that was displayed in the edit suite. You have, you take it to the device, you decode it, you make sure nothing screwed it up in the decoding process. You pass it through the YNB conversion, you put it on the display. You have to know the characteristics of the display. This is obviously effed. This can't work. We're trying to make it work anyway, and for that is the whole point of this talk, is I come to you to introduce the product of all of our efforts. which is test
New
cards.
Macbeth chart.
Yeah, no, I mean, all of this is in fact digital. So if I've done this correctly with all of my tabs here. So this is a test card. This is a cool test card. One of this is testing matrix conversion. So this is one of the first ones that we built. And the test card, you'll see it change. Watch the boxes on the bottom. So you've got the reds and the greens. Did you see that magic here? Now the reds have this inner box and the greens don't. This means that the card is being displayed using the Rec 709 conversion matrix, which is proper because it was flagged that way. And so what this test card does is in the reds, there are colors that sit within the valid RGB gamut when you YUV encode them in Rec 709 that are outside if you interpreted those values as Rec 601, they would be clamped. They would like decode to negative or more than 255. So in a correct value, they would, the colors would, in 709 the colors merge, the colors are distinct. In 601 they merge because they get clamped. The same is true for the greens except for a color that's valid in 601 and not 709. And you see when we seek in Chrome that the 601 matrix is used because somebody had searched on the internet RGB conversion matrix and plugged that into Chrome source code and then taken the YUV data, and so there's a separate one. So we thought we had fixed matrix conversion in Chrome. We got this test, somebody complained about it, we were able to identify the bug. So we actually think that we might make progress with tests like this. This bug has been fixed in Chrome 49. This is Chrome 48. So that's cool, like we're actually doing this. And then the real kicker here is this. This is the one I'm most proud of. This is the Metameric test cards. So this really tests Metameric instability. And you'll see a little bit of difference between the top and bottom colors here. And that tiny bit of difference is because the projector isn't quite right. This is not using true 709 primaries, and you can tell.
I don't think it's using true anything.
Yeah, it's not. Bless its heart. But you can see like something's a little bit off, but it's mostly right, and you know it's mostly right because the colors look more similar than their constituent colors, which if you actually zoom in, you see that the colors that made this up are actually really different from the colors above. So the way this test card was constructed is basically a brute force search. We created something in the LAB space and then created virtual primary pixels by using the individual colors here to approximate like what it would be to make that color using 2 pixels that were close to the other color in one color space. But because XYZ, because the additive properties of RGB colors and XYZ colors are not Euclidean, we can perform that operation in the human eye as compared to using the RGB substrate of the screen. And if they don't match, you see a color difference that's stronger or weaker depending on how messed up things are. And so we think these are pretty cool. I think these are pretty cool.
So, but you have that in an image in a certain color space. How do you ever make sure that you distribute that in a way that it's going to be represented in the same way, either in digital or in print or in any other medium? How do you ever make sure that anyone else is ever going to see the same colors that you see?
The idea is what we do is we tag our files correctly. We know we've tagged our files correctly, and we know empirically that the results of these files should be correct because we've tested them, we've looked at all of the color spaces, and if anybody opens it up and the colors don't match, something's messed up on there.
Right.
So it's actually a way to go through and finally burn everything down and get to, oh, there's a problem here, there's a problem here.
But if anyone else ever gets that and resaves it with a different color space attached, suddenly it's broken.
Right, and
hopefully
you can tell,
you know it's
and you can tell.
broken, yeah.
Well,
But
yeah,
then
I mean,
if someone prints it out and shoots a chart of that.
right, and then you can tell that that's broken. Like it does,
But
it
you
has
don't
to
know
be
if-
perfect at every
Right.
step.
But you never know if it was the print that was broken or the digital capture of that print that was broken.
Well, ideally, I'll just give a bunch of tech talks on it, and everybody will know at every stage. So that, 40 minutes later, that is the point of it, is that chart. And actually, I think that is the last slide. It is.